Welcome back, class, for the lecture on applied computer vision. Last time we were discussing the Hough transform, and we used this technique of voting and the transformation to find the lines in the image. So we saw how it works, and this time we will carry on this same discussion. And we saw last time, if you remember, that if we have 2 points in the image space, those 2 points will correspond to 2 lines in the Hough space, and these 2 lines will intersect because they are line, so they will only intersect at one place. They are not parallel to each other, they will intersect. So they will intersect at only one point, and that point will correspond to the line that passes through these two image space points. So it will be this line that passes through these 2 points. So we discussed, based on this technique, we are using the voting mechanism where the set of points in the edge image, they are represented by the to vote for the bins that they consider valid, that they consider represent their lines, and in this way overall the voting occurs, and finally the bin with the maximum vote wins. This type of mechanism is very dynamic because it will automatically remove all the noise, because it is highly likely, and it occurs like this, that noise never concentrates on one bin value. Noise will be random, so noise will never be focused on one bin, and hence we will only get the best answer for our set of points in the edge image that we want. Now there are some issues with the line representation. If you remember what equation we have used, so if you think before we implement this whole mechanism, there are some issues with the representation of lines. Okay, the equation we have used till now for the line representation is equal to this: y equal to mx plus b or c. Okay, now there is a problem with this equation. We discussed last time that if the line is like this, it has a positive slope. Okay, and if the line is like this, it has a negative slope, and if the line is flat, it has zero slope. Okay, but there is a one big problem: if the line is vertical, it will have an infinite slope, and we will not be able to use this equation if the line is vertical. Now this is a big problem, very big problem, because we cannot guarantee that in our image the line will never be a vertical line. So such equation will be undefined for vertical lines because the m is infinity. So we use to solve this issue, we used another more robust approach, which is the polar representation of lines. Now this equation that you saw over here, against this representation, there is another representation. We call it the polar representation for the lines. The formula is given like this. The concept is simple. The idea is shown in this diagram. If you look over here, each line, any line you want, any line, it is represented by two values. So remember, previously we had the line that was represented by two parameters. So parameters at that time were m and b. So m and b were our parameters. If you know m and b, you can draw the line. Yes? Same thing here. You have two parameters, but this time the parameters are quite different. So what we suppose is that, let's say this is your line. Okay, this one over here is your line. Now this line, we consider another line which is perpendicular to this line. perpendicular word is important. It is perpendicular 90 degrees, and this line connects L1 over desired line to the origin 0, 0. Okay, so we connect this line L1 to the origin by a perpendicular line. The important point is that it should be perpendicular. Okay, so it should be perpendicular. So we note down the length of this line and we call it, let's say this is a constant, it's called a rho. So this is another special symbol, rho, which represents the length of this line. Okay, and this perpendicular line, it will have some angle created that we calculate from the y-axis. Okay, so we calculate this angle from the y-axis and we use it, we call it this one as theta. So we have now two values or two parameters, rho and theta, and if we know these two parameters, we can draw any line in our system. In our coordinate system, we can draw any line. So you can ask me, for example, any line. Let's say you say there is a line like this. Okay, so to make a perpendicular line for this, you extend this line, take it up. So now at this location, it is perpendicular to your rho line. So now you note down the value of rho. So rho is not p, it's different. Okay, and then you note down the theta. In this case, theta is obvious that it is 90 degrees. So you note down rho, whatever is the distance, and you note down the theta. These two values are enough to draw this line. Okay, so this is a polar representation. Why we call it polar? Because over here we are using the values over here of theta, the angle, and because of this it is different from the previous representation of y equal to mx plus b. Okay, so we are dealing with now with angles over here. So polar representation, the polar or normal representation of straight lines is given by this equation. So the line that you will create, it has this equation. Okay, x into cos theta plus y into sin theta equals to rho. So rho is written like this, RHU. So each point in the xy plane, it will give us a sinusoid in the rho and theta plane. Now again, it is the same story as we saw last time. On one side you have the image plane, okay, or image, we use the word image space. You can call it xy space also, or xy plane. Okay, and on the other side over there we had the Hough space or parameter space. This time over here we call it, so that more accurate name at that time was MC space maybe, because these were the two parameters. Now here we have two parameters, rho and theta. So we use these, and these two, the point over here, for example, if there is a point at this location. So remember, in the previous case, a point in the image space was a line in the MC Hough space, but here a point over here, it will represent one equation, one function in the rho theta plane, and that equation is represented by a sinusoidal wave, sine wave. Okay, one point will be represented by one sinusoid and another point will be represented by another sinusoid. Okay, and these 2 points, same story, these 2 points are connected by a line. So this sinusoid will intersect at some location. Now the sinusoid will be intersecting more than 1 points, but both these points will give you the same line. Okay, so it will give us a sinusoid in the rho theta plane, and each curve in the figure, it will represent the family of lines that pass through a particular point in the xy plane. Okay, so over here each curve, it will give us, each function will give us over here a point on this plane, or you can say it's a line which is passing through a single point. So here you see the example. You have got these 2 points, xi, yi, and then xj, yj. Corresponding to these 2 points, there are 2 sinusoidal waves over here, 2 sinusoidal functions, and these 2 sinusoidal functions, they are passing over here through one, they are intersecting at one location, and this location gives us the values of our desired values of theta and rho. Okay, so you can pause it, you can think over it. That is an important point, you must understand it. So the intersection point, rho prime and theta prime, it will correspond to the lines that pass through those 2 points. Okay, so it will correspond to the line that is our desired line. A horizontal line, so now that problem is resolved. For example, if a line is like this, okay, so the rho and theta values will be like this. For this line, the theta value will be equal to what? 0. Okay, so that's what is shown here. A horizontal line will have a theta 0 and rho will be equal to the intercept with the y-axis. Rho will be the value you can measure how far it is from the origin. And a vertical line, which I drew earlier, so vertical line, this one, so it has the theta equal to 90, whereas the rho will be equal to the intercept with the x-axis, where it cuts the x-axis. Clear? So this is the polar representation. So with this mechanism, we use the same procedure. Rest of the things are almost same. So we do the Hough transform algorithm. How it works is that we use the polar parameterization, and here we have Hough accumulator array, which is like a big array that keeps the record of the votes. And what we want to do is that, so I think we don't go into this details of the algorithm. The concepts should be clear. What we do is that we keep tracks of the vote, how much votes are occurring, and a little note on the time taken. So time complexity we have been discussing in many cases previously. Time and space complexity, how much time it will take. And so this should be the clear for the people coming from after the course of algorithms. Space complexity, how much space or memory this algorithm will consume. It will be k power n. So where n is the dimension, or means the image dimensions. Normally, for example, here you have 2-dimensional image, and then you have got the k bins, how many bins are used. Okay, so if the number of bins are more, it will take more space to store the votes. Time complexity, it will be over here. It will depend on the number of edges. So overall, time complexity will not be extreme. It will correspond to the number of edge pixels. Each pixel will be voting for, each pixel will be used to draw one line, and there will be a voting associated with it. So you see over here an example. In the image space, you have a straight line edge. So this straight line edge, when in the polar representation, each one is going across, each pixel, it draws a sinusoidal wave, and these waves are crossing each other at many locations. You can see many of them. But practically the most bright point is very obvious. There is only one point which has the maximum votes. So bright value or bright vote value means a high vote count, and the rest of the areas which are black have no votes. This is another example. If you see over here, we have got a square. So in the image there was a square, in the edge image there was a square, and that square, because remember a square has got 4 lines, so each line is represented by one dot. So you see, one dot represents each line. Here is another example. So there are a couple of lines. I don't know how many, depending on our threshold, how many lines will be detected. You see, hopefully at least 3 I can easily find, maybe 4. So here I can have 1, 2, maybe 3, 4, or even more, I don't know. But these are the set of lines that can be detected from the edge image. So leave the code. We will go and work on our own code in Python. So here is another example. So this is the image of American football. So image of American football is first transformed into edge image, and then from the edge image we try to extract these lines. So in the case of lines, there are a lot of these values that are coming out, and when they are used to trace on the image, they come out something as these lines. So you see, some of the lines are small, some are large, and so it's just like you can see large number of lines are detected in the image. Clear? So maybe you can pause it and think over it. If something is not clear, ask or search on the Google. So now a little bit more on the other side. Let's say there is an edge image. So the edge is not smooth. So now this time you see an edge which is noisy. So noisy edge are possible for many reasons we have discussed already. So you see, what will be the result? The result of voting from this mechanism will give us this thing. Okay, so it will give us a bad voting pattern, but still the votes, they will be in the same neighborhood, in the same area. With little bit of difference, they will be in the same area, but they will not be converging on a single point. So to solve this problem, one thing that can be done is that maybe the bin size can be increased, the voting bin size can be increased. Then all of these points, or most of these points, they can vote for the same bin. So you see over here in the image space we have x and y, in the Hough space we have got this theta and rho. Here is another example. This time the noise is so much, practically there is no line over here. You don't see any particular line. Okay, so when there is no line over here, you see some scattered results, but you don't see a very bright specific pattern. Now it depends on your threshold value to select some value as a line or not. Maybe from this image you can try to infer some line. Maybe this is a line, maybe this is another line, but it will be some smaller broken lines, not a very strong candidate line. Clear? So leave this over here. What no, we don't leave this, but here are some other extensions given. So extension means that what improvements we can do further. One improvement that's given is that what you can do is that Now these are some advanced things, advanced topics, just to give you an idea. Okay, one thing that can be done is that in the voting mechanism, maybe you can give more votes to the edges that are more stronger. So for example, if the one edge pixel value is very bright, okay, it was detected with the value maybe 250, whereas another edge was with a value of only 55. So they shouldn't be equal. Okay, so you can implement some sort of method where a very bright pixel value, maybe it represents a very strong edge detected, so it should be given more weight, more vote value. So votes are not like discrete values 0 or 1. It can be a big number, maybe from 0 until 10. So the brightest pixel can cast the vote of 10 values, whereas if the value is very small, it can give a vote of 2 or 3, like this. Another thing that can happen is that we can change the sampling rate to increase or decrease the resolution. What does it mean? Let's say you have got an image and it has got a line like this. Okay, so these are the pixels. It's up to you that you can skip some of the lines, some of the pixels. So let's say I change this. So you select one pixel, then you omit one, then you select another one, and then you select another one, and like this, skipping one pixel. When you are skipping the pixels, basically you are reducing the quality or resolution of overall your edges. So basically you decrease the sampling quality of the edges. What will be the effect? For example, your line was broken for any reason. It is very noisy and it's broken. It's like something like this. Somewhere the pixels are missing. So if you are using less number of pixels or you leave the space in between, maybe you have a chance to more generalize the line. Don't focus on the all the pixels, but only try to focus on the values after some gaps. Okay, so leaving one pixel, selecting the next, then leave one, then selecting the next, like this you will be focusing on the overall pattern of the line. Similarly, we can do the same thing. The same ideas that we have seen over here, we can apply them on other shapes, which can be like circle or a square or any irregular shape also. Okay, so we will go through the circles, how we detect and transform the circles. For the circle, normally when we want to do the Hough transform, for any circle we need to know two things. One is the center of the circle and the other is the radius of the circle. Okay, so the center of the circle, it is basically 2 points x and y. So here we say we have two values a and b. So if you know a, b values and then you know the radius of the circle, then you can draw any circle with these equation. Okay, but remember we are considering the circles with the same radius. We keep it fixed radius. Okay, so here if you see, the theory is same but maybe a little bit tricky. How it works, remember over there what we did? If you remember, we for the lines what we did was we select a point in the image space and that point used to select a line. For example, this point in the Hough space, it represented a line. It said that okay, this point over here, it represents all the lines that are passing through it. Okay, then there was another point. Okay, it was represented by all the line, another line. So all the points on this line, basically they pass through all the points on this line, they represent lines here and they pass through this point. Okay, so these two lines, they intersect at one location, and that location is the line that will connect these two. This was the theory for lines, okay, not circle. Here the theory pattern is same, only some things change. Over here I have got a point. This point over here in the Hough space, it is represented by all the points that lie on this circle diameter, on the boundary of this circle. Okay, all the points. So what does it mean is that all the points on this boundary, infinite number of points, they represent infinite number of circles in Hough space. Okay, and all these circles, they pass through this location. So maybe there is one circle like this, another one like this. All of them, they are passing through this point. Okay, that's the theory. All of them, they pass through the all of them, they must share this point somewhere. Okay, so this is one point. So for one point I have one circle. Similarly, there is another point and it will have another circle. Okay, and then there is a third point and third circle. So basically these three circles in the Hough space, they represent over there the whole set of circles that are passing through, that have this point, these 3 points included. Okay, so you can pause it, you can think over it. The theory is same. Over there we had lines, now here we have circles. Okay, and all these 3 circles, they will intersect at multiple places, but all the 3 circles will only intersect at one point. Okay, and that one point will represent one circle. So remember, a point in the Hough space will be a circle in the image space. So that one point in the Hough space will represent one circle that will contain all these 3 points. Very important. All these 3 points will be on this one circle, and that circle is represented by this dot over here, this one. Clear? Remember, this whole discussion, it is based on one very important rule, one very important point, that the r is not changing, the radius is fixed, and it is known already. Okay, we already know the size of the radius of the circle. Very important point. Okay, so we don't know what is the center point of the circle, but we know what is the radius of the circle, what is basically the size of the circle. That's important point that we consider in this approach. So same story. I suggest, if not clear, go back to the images, and over there you see the transformation between image and Hough space, and then come back here, and again we have same image and Hough space story, but the difference is that in the image space, a point in the image space, a circle is represented by a point in Hough space, and a point in the image space is represented by a circle in the Hough space. Okay, so this is what is happening. Each point, these white arrows, they show that each point in the image space, it is represented by these green circles in the Hough space, and there will be one intersection of these 3 circles. Okay, only one intersection. So most votes will occur for this center point, and this point will represent one circle, which is the one that we saw over there. Okay, so basically the point over here, it will give me effectively this center point, and because the radius is already known, so this center point I can draw easily a radius. Okay, so go through it. If you have questions, you can ask. Here is the example how to detect the circles with Hough transform. And you say this is the for the bowling game. Over here the algorithm it detects over here this circle, and also the box, the crosshair indicates the result of the Hough transform, and the bounding box it is also finding over here this circle also in the shadow. Okay, here are some more examples. This is the example we will also consider in the lab. So here is the image. We will be using almost the same image, I think. So this image over here, it is about the coins. So these are the American coins. Over here you have got the penny, smaller one, and this is for 25 cent, I think. This is the quarter. Okay, so this is I think 5 or 10, and this is quarter. So you transform it first into edge image, and then you try to detect. Now remember the important point, you already you should know the size of the circle, okay, the radius. So for the penny I know the size of the circle, so first of all I apply the algorithm only for the penny. So when I apply the algorithm only for the penny, I get only one bright spot, one bright dot. Okay, the others are not bright, other three they are not bright. Okay, so this is it for the penny, and then you change the radius, and this time you apply it for the quarter, and quarters coins are bigger, so but they are all three same size. Okay, so you apply it this time on the quarter, and this time you get these three results, you detect it. So you give the size, you will detect the circle in the image. Okay, so this is it. When you superimpose your image with the result, you will get exactly same location perfectly. When the circle size is not known, the radius is not known, that is more involved, that is more tougher theory. We will not go into that one for now. So here is some code given, leave it. So leave this one also, practical tips. Leave it. And Hough transform, what can be the good and bad points for the Hough transform? Now this is good, this is a good point, important. The good point or the pros for the Hough transform is that all points they are processed independently. Okay, so every pixel in the edge image it votes independently, it does not care about others. Okay, so if there is some sort of occlusion, so what is occlusion? We saw it in somewhere in first or second chapter. Occlusion means, in the term of image processing, occlusion means one image is hiding behind another image. Okay, so for example, if you have edges like this, and some part of the edges they are hidden because of maybe some shape in front, so some part of the line is hidden because of this. So you can still, if this blocking, so occlusion is basically blocking, if this blocking image is not so big, then you can easily take care of that, because you are detecting a line over here, and you are detecting a line over here, you can easily infer the overall line. Okay, so this is a very good point related to independence, independent voting. And there is some robustness against the noise also when the voting is done independently by the pixels. This technique is overall very good against the noise, because noise points they never contribute consistently to any single bin. They will never vote to a single bin, but noise is random, so it will vote to the random bins, but overall the bin that will win will be the best option, which is normally the correct option. And this type of approach, it can detect multiple instances of a model. So if there are 10 lines in an image, you can detect all those 10 lines in a single pass, in a single go. So you don't have to, if you have 10 lines, you don't have to run the algorithm 10 times. Okay. So in a single pass, you can detect all those lines, multiple instances of that model. If it's line, you will detect it. If it's a circle, you will detect it. Okay. What are the bad points and the cons? Complexity of this algorithm, the search complexity, the search time increases exponentially with the number of model parameters. So if you are searching for line, if you are searching for circle, square, rectangle, oval shape, if these parameters models are increasing, then your time will increase exponentially. Remember, exponential means something like we saw previously somewhere, for example, like this, b power d or 2 power n. These are exponential, and this is very high cost. So it will increase when your model elements increase, the number of model elements. Also, there is another bad point that can happen related to this algorithm, is that non-target shapes, they can also produce some spurious peaks. Some random peaks they can produce in the parameter space for the targets that you were not expecting. Okay, you are, for example, trying to detect a circle, and there is some shape in the image. You don't target it, but it resembles a little bit with the circle, and maybe it will give some bright spot. Similarly, you were targeting a line, and in the image there is a part of the curve that is a little bit straight, and that will try and that will behave as a line. So it will be a bad result for you, because you did not want it that your curved line is detected in your algorithm as a line. And another one is it's at times difficult to select the size of the grid, how much will be the image size, because using the whole image, maybe the image is very big, using it completely for object detection, maybe it's not suitable. So how much size of the image at a time, how much window size you will use, it's hard to pick. So this is it, the Hough transform, and then the next one we don't cover it, but it's about irregular shapes. You can use the Hough transform to detect irregular shapes. There is a huge lot of theory for this. So now we will go back to the lab side, and we will see over there the lab work. So come to the lab side over here. So we will load the CV2. So again, remember the points I have mentioned again over here, just for revision, that Hough transform does not work on the original image, it works on edge images. So you use, for example, Kenny edge detection, and then we will use the voting mechanism. So how we detect the line, first of all. So first part of the lab work is detecting lines in the image. So what we do is that we load the original image, and we try transform this to edge image, and then we use the function in OpenCV, it's called HoughP. Okay, and I think HoughP or Hough lines P. So let's go. Here it is the image of you remember the image Frumer. We convert it to the Kenny edge detection algorithm. Here it is the result of Kenny operation. So this is the edge image. Now we will be using this function. This is Hough lines P, not HoughP. Okay, Hough lines P is an image is a function in OpenCV that you will provide it these arguments. You will provide it the edge image, and then you will provide it the accuracy, the minimum unit. So remember, here we are dealing with the polar representation. So these algorithms, they implement polar representation, not the other one. Okay, so here we are using the first argument here, and the one is row accuracy. Row accuracy means what is the minimum unit you can have for the row value. So remember, row is the length of the line that is perpendicular to your desired line. So what is the accuracy? Usually it is the minimum value 1. Okay. Then you have the theta accuracy. Theta accuracy is given in radians. So if you remember in your mathematics courses, radians is equal to pi over 180. So you will basically convert your 1 degree. So you want the accuracy of the angle to be 1 degrees, and 1 degree in radians is given as pi over 180. If it's not clear this theory, go and search on the Google, you will see easily. 1 degree is equal to pi over 180 radians. And then you give the threshold values, and threshold value here is basically which line you want to detect. How much should be the range of the line that you want to select? Above this, you will select the line as a valid candidate for the from the votes. So here it is. I use it half lines p edge image 1 and pi over 180. Then I give this value 80. This is the minimum number of votes. If my candidate gets 80 votes, then I select it as a line. If not, then that's not a good line. So I run this. And if you look over here, I defined a variable lines. So this lines variable, it now contains 3 arrays. Each array corresponds to 1 line. Okay, so you see, this is the starting of the line, this is the end of the line, and so on for the others. So there are 3 lines inside this variable. And you can use this small code. There are 2 for loops. One for loop goes through these lines one by one, the outer for loop, and the inner for loop will go inside each line, and it will draw the from the line, it will pick the 4 values x1 y1 x2 y2 and draw a line on the image. So we have done it before. So here it is. You can use the CMap also if you want to make it gray, but these are the lines that are drawn. The yellow ones are drawn because here you see, you can change if you want, make it a white line. It's not shown white because I think again the same problem of the conversion, color conversion. Okay, so here it is. The 3 lines are detected. These are the 3 lines you see over here. I hope it's clear. So this is it for the lines. Now coming to the circles. The image is given for the circles. It's an image called, for example, it's the name is coins2.jpg. Load the image and then we transform it into edge image. Remember here I use this high value. If this value is kept low, then there will be too much noise in this image because of the background. You see in the background there is some sort of cloth which is very rough, like jeans cloth. So because of this cloth, there was a lot of noise in the image. So I tried to reduce this noise by tuning this parameter, taking it very high. So you can practice test with different values. I get this edge image, and from this edge image what I am doing is that I provide over here this function Hough circles. I provided the edge image, and then there is a constant given Hough gradient. This is the only constant available. It does not change, so just don't mess with it. And then you have over here, let me see what were the arguments. Let me put it somewhere. Hough circles, and let me search. They haven't given it the, so this is it I think. No, this is Kenny half circles, this one. Yeah, this is it. So I should put it somewhere in the slides. So here it is. So what it shows is that you give the image, you give the method, and what is this DP? So method is basically the detection method to use. There is only one implemented method available for now, which is CV half gradient. So we don't mess with it. DP is basically the inverse ratio of the accumulator resolution and to the resolution to the image resolution. So this is something constant. We also don't, I think, disturb it. So we will keep it, I think, 1. So I think it's 1 over here, okay. And then what we do is the minimum distance between the centers of the detected circles. If the parameter is too small, the multiple neighbor circles may be falsely detected in addition to a true circle. So you want to show, for example, that if the circles they can overlap, come on each other, on top of each other, but if you put some gap, the circles, it will try to find the circles only if they are far apart from each other. So here they have given. So this is important. If you don't give a value, it will try to detect 2 or 3 circles at the same location. So be careful with that. So this minimum distance is a good parameter. And then there is parameter 1 and 2. First, method specific parameter. If the higher threshold of the two passed to the Kenny edge detector, the lower one is twice smaller. So these are the parameters, minimum radius and maximum radius over here. And you give the minimum and maximum. So here they have given it a 0 value, both minimum and maximum. So we don't detect the radius. We are only focusing on the center point. Okay. So here it is. With this approach, over here I detect only 2 circles. Okay. So these 2 circles, I will draw them. So to draw these circles, first I convert it into unsigned integer, the center points, and then I use it to draw 2 circles, the points. That's why it was. So it is considering the old image. That's why it draws 2 circles, because these are the 2 circles that it detects, the 2 wheels of the car. Whereas for this image, let me run this image. It will detect how many circles? 3 circles. Okay. So somehow it is detecting these 3 circles, but this one is not detected, the middle one. Okay. So this was it. This was the Hough transform, and we used it over here. So over here, the parameters that we will be focusing is the edge image. This is constant, don't disturb. This is 1, don't disturb. This one shows the distance between the pixels. Maybe the fourth circle, but fourth circle is not so clear. That's why it's not coming. So fourth circle is not complete in the edge image. So try maybe to change these threshold values in the Kenny, and try if you can get this fourth circle. Only then you will see it over here also. Okay. And another thing is that if the circles are too close to each other, then this value will affect the answers. If the circles are too close, then this 20 value will not detect the circle that is too close to another circle already detected. Okay. So use that, and radius we don't detect and we don't draw it. For now we only focus on detecting the circles, not the drawing the circles. Okay. So this is it. This is the Hough transform we did for your practice. Always we do something for the practice. So let us take the edge image, for example. So we have limited options for the circle. So there is one circle, there is one image with circles, and another one can be, and take this one, frizzy maybe. So this is interesting. Maybe you can take this frizzy, and it has got two eyes. Maybe they are circle, and the eyeballs, I don't know. Let the image open, and then we will see. So use this one. I'm not sure if the eyeballs they will come as circle or not, but the outside is perfectly circle. So you should detect at least two circles from the frizzy image. So try to detect it, and you have to do this work. I will check it after our vacations. You have to do it in the exercise area, this frizzy. And the second work that you have to do is, for example, also try this one, bicycle. Bicycle, or maybe fruit. Fruit is not circle, no. Bicycle. So try the bicycle also. Frizzy and bicycle for the circle. And for the line, you try to use these two images, football and this Brooklyn Bridge. So these two images, you try convert them into edge image, and then you try to see how many lines you can get from these images. So this is our second and last part of the Hough transform. Next time then we will move on to the next topic of geometric transformations.